Okay, let's try to calculate beta. Remember what is beta? What is beta? It's a type 2 error. Okay? It's in your cheat sheet. When you reject the null hypothesis, when it's true, you are committing type 1 error, and this is equal to alpha. And when you do not reject the null hypothesis, when it's false, then you have the type 2 error that is beta. So the beta is when you do not reject the null hypothesis when it's false. Okay? So how do you calculate that? Well, basically, you have hypothesized distribution, if you will. Okay? And in the hypothesized distribution, you have the mu from the hypothesis, right? And then let's say that you have an upper tail test, so this is alpha. What is beta? Well, in order to find out what is beta, you need to know what is the real population parameter. So let's say that the real population parameter is over here. This is the real, right? This is the hypothesized distribution, and this is the real distribution. What you need to do in this case is to find out what this value is. Okay, this value over here, and this is beta. That's it. What about when you have a lower tail test? If you have a lower tail test, and if this is the real hypothesis, then if this is alpha, this is beta. You see? This is the hypothesized, and this is the real one. And if you just translate this over here, this is beta. Okay? Why? Because this is the do not reject zone. So, and beta is the probability that do not reject when it's false. Basically. What happened in the two-tailed test? I have to do it right here in order for you to see it. Let's say that you have this situation when you have a two-tailed test, but the real thing, this is a hypothesized distribution. Let's say that the real distribution is right here. Right? So the beta in this case is equal to what? To this. This is alpha divided by 2, and this is alpha divided by 2, and this is beta. Remember that you transfer this value over here, and you transfer this value over here. So, in order to find out what beta is you really need to know, again, this is the hypothesized from the null hypothesis, and this is the real one. This is the hypothesized from the null hypothesis, and this is the real one. Probably your book treats this more complicated, but it's not that like so. I mean, remember that beta is the probability that do not reject. So you have to deal with the not rejection zone, and that is why it's in the left. This is in the right because it's the do not reject zone, and this is in the middle because this is the do not reject zone. Okay? For this section, you only have one homework problem. So, although it's not, unimportant, but it's more important for you to really understand the rest of the chapter. So yeah, it's important, but it's not as important as doing hypothesis testing. And again, the first thing that you need to do is to formulate the hypothesis correctly. Anyways, let's do a problem for this section. Okay, 933. We have the following hypothesis. Mu is greater, another hypothesis that mu is greater or equal than 75, and the alternative hypothesis is that less than 75. Again, the null hypothesis always has to have the equal sign. Equal, greater equal, or less than equal. If you see the other thing, or you put it in the other way, is totally wrong. Okay, this is the hypothesis. So, given that sigma is equal to 15, n is equal to 36, alpha is equal to 0.01, calculate beta is equal to what? In the two situations, let's do mu equal to 66. When the real population mean is equal to 66. They have two, 73 and 66, but let's do 66. Okay? So what is the value of beta? Okay, again, this is a what? Upper tail, lower tail, or two tail? It's a lower tail, right? It's a lower tail test. Okay, and alpha is equal to what? 0.01. And the standard deviation of the distribution is sigma over square root of n, and that is equal to 15 over square root of 36. So, right? Because we're dealing with a sampling distribution. So we have a distribution which is 15 divided by 6, 2.5. So the standard deviation of this distribution, whose mean is equal to 75. This is the hypothesized distribution. Right? So what is this value over here? What is this value? If that is 0.01, I mean, we are dealing with a standard distribution. It's not the normal standard distribution. In order to find out what is this value, of course you need to know what is, either you use your calculator or you have to go back and forth from the standard normal distribution. Okay? If you do the way you like it to do, you know that for Z is equal to 0.01 is 2.33, right? Negative 2.33. Okay? But what is the value of X? Remember the formula? Z is equal to X minus mu divided by sigma over square root of n. Or sigma. Okay, sigma, because it's already sigma of X bar. Okay? So what is X? Is equal to Z times sigma plus mu. It's exactly the same one. You multiply these both sides for sigma of X bar, So it goes away, this one, and then you add the mu, and goes this one, so x is equal to this sigma plus mu. Your book says that x is equal to mu plus z sigma x bar, which is exactly the same. Exactly the same.
So that's how you get the 75?
Yeah. No. This is how you get this value over here. No, the 75 is the hypothesized mu.
Oh, okay.
You see? That is distribution where the mean is equal to 75 because that's the hypothesized mean. Okay? This is the mean that is in the hypothesis. Okay? So what is x? X is equal to mu. What is mu? 75 plus z, but it's negative 2.33 times 2.5. So this value over here, if we translate it into this distribution, is equal to what? 2.33 times 2.5 negative plus 75. Is this value over here is 69.18, if you will. So this value is 69.18. Yes?
Did you say there was a way to do that with your calculator?
There is a way to do it with the inversed, go to distributions, inverse normal, okay, enter. When you get the inverse, you give the calculator the probability, the left side of the probability. So in this case it's 0.01, comma, and then you have to give the calculator mu and sigma, comma, 75, comma, 2.5, enter, and you're going to get 69.1841. So exactly the same. So with the inversed normal. And again, if you use the inverse normal, when you use the z, you don't enter the mean and the standard deviation because the calculator assumes 0 and 1. But if you have this distribution over here, I mean, you can get this value directly from the calculator. 69.8. Exactly. Okay? But I do it this way because I think that you like this way. But you can do it with this. Anyway, so I have 69.18. So 69.18 is this value over here in this distribution. So what is beta? If the real thing is what? 66. The real population mean is 66. So the real population mean is up here. To the left. This is 75, right? But the real is 66. What is the standard deviation? It's exactly the same thing. Sigma over square root of n. 2.5. So it has exactly the same thing. I mean, the same standard distribution. But it's shifted to the left. Okay? So what is beta in this case? If I, let's do this. If I translate these values into this distribution, this is my beta. Okay? What is this value? Is 69.18. That's beta. And I want you to look at the graph. Remember when I told you that when you increase alpha, you decrease beta, and when you decrease beta, you increase alpha, and vice versa, right? So it goes in the opposite direction. Look at this. If you increase alpha over here, of course you decrease beta. Okay? And the other way to do it is by increasing the sample size. So this distribution, if you increase the sample size, this distribution would be taller and thinner such that my beta is low, is small. Okay? But that's how it works. If you increase alpha, of course you decrease beta. If you decrease alpha, you increase beta. Okay, so what is beta? If you want to do it your way, you have to get this probability. You have a normal distribution with the mean equal to 66, standard deviation at 2.5, and what is the probability that this stuff is greater or equal than 69.18? And that's pretty easy, but you can do it using your calculator. Okay, go to distributions, go to normal CDF, cumulative distribution function, okay? And then you have to enter the lower limit, the upper limit. The lower limit is 69.18, comma. The upper limit, the positive infinite, let's do 300. Okay, 300, comma. What is the mean? 66. What is the standard deviation? 2.5. Enter, and that is equal to 0.102. 0.10168, whatever. So 102. So when my alpha, when in this situation, my beta is equal to 0.1. You see? That's it. Any question? Did you get the process? I mean, you have the hypothesized distribution, you get the real distribution, and you have to deal with the do not rejection in this part. Do not rejection, because beta again is the probability that do not reject. So you have to deal with the do not rejection zone. So that's why it's in the right side. Do not reject when it's false. Okay? The problem in your homework is very similar, but it's an upper tail test, but it's exactly the same. So it won't be that hard to do it.